Hey there, Uncle George and TA in class. This is Tony out in California. I'd like to try and do a quick video of my project for GPU computing. Um, this is going to be a more advanced extension. We're going to try and work on Linux here. Namely, we're going to try and work on remote servers and not just kind of an easier home setup where you may have one small GPU and it's pretty easy to allocate some work. Here we're going to go for some Tesla servers, namely the Luke Tesla server, and see if we can get things to compile and run and work on multiple GPUs, multi-threads, multi-streams, and just use the full power of parallelism if we can. So again, we're getting away now from single GPUs and single streams to the most complex, advanced thing we can do, which is many devices, coordinating many devices. So what we're going to do is, since I have a background originally in finance, it's easier to me to kind of think of finance problems, which aren't always super useful, but they can be challenging because finance problems can involve a lot of math and also very large data sets. So we're going to look through lots of price data and see if we can test, get some simple measurements and test a simple pattern called a kind of a stat measure, amongst other things, called a z-score. And if that z-score can lead us to think of z-score as a factor, some kind of predictive factor that can help us to figure out the future price of future direction of prices of markets, and then maybe lead us to some excess returns. So the factor is trying to predict excess returns on stock indices, commodities, whatever it may be. And since we're going to have many markets and large chunks of data, we're going to need to divide this work up amongst GPUs in terms of markets, and then stepping through the data, kind of coordinating everything, and syncing and whatnot. So for those of you who are kind of brand new to or newer to the GPU stuff, it's called hybrid computing, and we're just simply sharing some work on the CPU and then sending other simpler math things to the GPU. GPU finishes and then sends it back to the CPU, and rather than doing it all on the CPU, which as the professor has said, is the older von Neumann model. So we have to kind of get away from that now because the problems are just so large. We'll also explore some non-C, C++ approaches using wrappers, namely in JCUDA and MATLAB. So we're kind of going on want to go beyond the traditional C++ approach here. So again, we have this is code in C for simple one device, one device, one GPU, one stream. So we're doing multi-threading on one GPU, but really it's not the full power of what we could do. Once we're dealing with multiple streams and multiple GPUs and multi-threading, we can really try and boost things up a bit. So just to show you a simple program here, again, we've got some stuff in the preprocessor, just quick functions. It's a lazy way to make some functions kind of quick. We have some paths for output and input, and we need to divide the data into steps of years, if you will, 377 days, and this will come in later for optimization. So every 377 days we are going to re-optimize the market, the parameters that drive the model, and we'll look back basically 5 or 6 years, or 1,597 days to help make the optimal decision. So again, in finance we often have these portfolio optimization problems where it can take up a lot of computing power. So it's not that it's rocket science, it's just a lot of data dependencies and very large sets of data. So the big thing initially in C, this is CUDA C, if you will, is an extension of C. It relies on some of the libraries that NVIDIA built. Of course, we are going to build our own functions later. It's kind of the whole point of this. But we're just declaring everything up here, and here's the main argument. And in order to accomplish all these sub-optimizations, we're going to have a bunch of for next loops that are nested. I wonder if I can catch that. Yeah. Outline maybe. Yeah, not really, but you can see a bunch of math functions here, and this is Eclipse. So Eclipse is very useful, and we're working in Linux here. But basically, here's inside the main function a bunch of for next loops. We have to, you can see they're all nested here. We're going to have to get every possible combination of the parameters. We call this exhaustive optimization, so we're going to try every combination and see, looking back on a subset of the data, what was the best, what was the maximum profit, and once we find that, we will use it for the next period forward, and we call this basically out of sample, in sample and out of sample testing. And if we come here, we could probably see this is HTML, but it's also a markdown format on Bitbucket, if anyone wants to look at it. It's just easier for me to get the pictures in the HTML, but yeah, if we look at this quick primer in finance, for this project, it's interesting. I had to show the code and also give a primer in finance for some people that are maybe new to it. Just kind of describe the problem. So just want to show you what a rolling optimization looks like. Yeah, I don't really see it here. Anyway, just remember we're going to have a lot of calculations going on, and the largest hybrid computing setup right now is Oak Ridge Labs in Tennessee. They did win back the supercomputing #1 slot from China. Then I think China just overtook them last year again. But you can see it's this is their setup. They call it the Titan. It's using thousands of NVIDIA cards just kind of linked together. But you see hybrid computing here, CPU, GPU. Here's Oak Ridge. Imagine the fun working in a place like that. Or Argonne Labs. It'd be a lot of fun to try and bring GPU computing to classic CPU-centric problems. So we can see the computing power here, teraflops and whatnot. Here's a quick, just simple description of the typical GPU server. Large scale, radically diverse hardware. Openness, not so open. These things tend to be pretty secure, the SSH and tunneling. Storage tends to be distributed file systems, and there's also shared memory, synchronous, asynchronous. Async just means, things are kind of being passed back to the CPU as they get done, no particular order. Syncing means to wait up until all the streams and threads are done and then push it back. There's times you want to use either or, but syncing slows things down. You can see these math and physics problems are getting tougher, that our data sets are getting larger, so we really need more hybrid computing. We need more computing power, and you can just see Oak Labs, their trend over the years. Used to have the Crays, CPU centric. Now they've moved to this hybrid setup here. So we just want to design some robust program. Again, we're going to use finance here. And then we want to run the program on single GPUs, multi GPUs, single streams, multi streams, different servers. We want to run it with wrappers and JCUDA and MATLAB, and also non-CUDA open source approaches called OpenMP or OpenACC. And we're just going to heuristically track all the time these things take, and we want to try and prove to ourselves that the GPU greatly speeds up a time by, can be 10 or 20 times, 30 times speed pickup. 300% to 3,000%. So it helps a lot. In the old days, you kind of be sitting there and waiting maybe many hours or days to get your results back before you could change your code and try and improve things. So again, a lot of this started with C, C++, so we have to get back into pointers or whatnot. No big deal. We have some quick primers here and examples, but this is basically it. Eventually, we're going to need a graph like this to keep all our results. But Amdahl's law, of course, is right here. How much can we really speed up a problem? Is it parallelizable to begin with? And that means we're going to have to use operations must be independent for them to be parallelizable, and that can be tricky sometimes. You can sometimes use some loopholes to make them independent. If they're not, sometimes you just have to wait. Part of it has to be sequential, and other parts you can do in parallel. So again, the highest level here is kind of doing the multi-threads, multi-streams, multi-GPUs. Parallelism doesn't just mean multi-threads. It's kind of a lot more than that. So and again, there are tools to help you figure out how fast your code is. Again, the Profiler from NVIDIA helps a lot. I'll just open this up. Again, these documents aren't complete. Some of the code's been written, some of the newer code has not been written, but we have to think about memory and shared memory and pin memory and all that kind of stuff. But yeah, let's keep going here. Let's see what we got. Yeah, so our model's simply gonna say, find all these stats, including z-score. Z-score will be the main trigger or factor, and say, hey, if the market is overbought and rich, maybe we should sell, or maybe not. Maybe we should buy. Maybe it's a momentum trade. Or maybe the market will mean revert and we should sell. We don't know. Part of this exploration is to find some rule that will help us in finance and do the testing as quickly as possible and just see what the results are. And very often in finance we're trying to maximize something called lambda, or the Sharpe ratio. In physics, lambda is decay or half-life. But finance borrows a lot from physics. If our math isn't good enough when we're younger, we drop out of physics and come into finance. I had to put that joke in there for Uncle George. But so things like lambda and omega and gamma, we have all those things too. Basically, we're trying to maximize the risk-adjusted return. So your average return divided by your standard deviation or volatility, that is the Sharpe ratio or lambda. So that will be our optimization rule, and we're going to do exhaustive optimization. You see these two sets of arrays or parameters. We'll have to combine these, basically 9 combinations there. When working with larger parameter sets, we could use something called genetic optimization, where we won't try every combination. We'll just try to start at a good place or a seed of 0 if we don't know, and then go from there. And genetic optimization is the fastest, but you're never guaranteed the best answer, and it isn't always able to be recreated, especially if you're starting at a seed of 0. So when in doubt, we actually like to do this exhaustive optimization, but it takes more computing power. And in this kind of simpler model, we just have a couple parameters with 3 choices each, right? But in the real world, there are many factors and many parameters, and you start running into hundreds of millions of combinations. And if you're fitting intraday to try and make a quicker trading model, you really start needing more computing power, and this is where it begins to add up. So it's just a sample of a rolling in sample versus out of sample test. Again, that's in the document. Yeah, and you can see even in a simple model, we already have 2.5 million optimizations to run. That's just one model. Nothing is perfect in life, so in the real world there will be hundreds of models being traded simultaneously. So that's really where this kind of computational problem starts hitting the wall. So we could run this simple program on my own GPU. It's not the most powerful one, but we just run one market here. This is multi-streamed and multi-threaded and blocks. GPUs are divided into blocks and grids, and processing caches. So we can talk more about that later, but we can just run a quickie and just see how we do. Did we save that? No, I really don't want to save changes. Yeah, so we just ran one market here, and we got some results. Some files were sent out with each test result. Remember, the data can be 20, 30 years long, so we're going to be stepping through, starting with 5 years forward. Need to look back 5 years, and then every 377 days keep looking back at the last 5 years and try all our combinations and get the max Sharpe ratio. So yeah, we see average Sharpe ratios here, and in sample is always biased. It's your degraded data. It's our cheating. We've gone back in the time machine and been able to figure out the best parameter combinations, and then the out of sample, of course, is your kind of fair to be expected profit. So you see it's roughly 50% of the in sample Sharpe, and that's a good rule. That loose rule seems to work, that heuristic. So yeah, so we basically have a bunch of nested for next loops, and let's see if we can find the actual CUDA function. We call them CUDA kernels. Yeah, we can see the asynchronous here, and we're communicating back to the host CPU and then the GPU. And here we see the classic CUDA kernel call. We see the triple chevrons here, and here we're just saying how many blocks do you want, how many threads, how much memory, shared memory, and which stream I we're in. Again, this is multi-streaming as well, and so we get a lot of things. Some data, we need to wait for and sync. CUDA stream synchronize here. Some data we can do asynchronously. And that's really trial and error. You want to go as fast as possible. But sometimes you get back zeros. You realize you haven't synced things up, so you're not waiting to get back your results. So anyway, and we keep looping through, and then we repeat for the out of sample test too. You can see all our math functions at the end here. This is matrix multiplication, just faster. It's another trick rather than just saying x times y. Again, vectorizing your code or getting things into running into parts of matrices is a good trick to speeding things up. So That's basically what a CUDA function looks like. Here's our regular C functions. Return, z-scores, signal to noise ratio, don't really need to worry about that. Opening files and whatnot. And of course our clocks to time things, right? We've got a lot of time here. Okay, so yeah, this is well and good, but it's easier running on your home setup. This is an advanced course, so we got to make sure we can run on a non-local server. And I've had problems in the past, so part of the challenge is to get that working. So see here, we've logged into Tesla at school, and I have some preliminary code out there, and you know, we're gonna just edit it and see what we got. Let's see here. Yeah, we just got one market there, but it's okay. There's the code. So we'll X out of there, and you know, we'll just run it, see if this even runs. Again, it's always harder working on foreign hardware that's not your own, especially GPUs there. So let's go to CD bin. Oops. No. This one, there's something there. So our output files, something looks like it's working. Can't find the source yet. Just go back to my local setup here. Go to workspace. There we go. Oh, debug. Okay. Yeah, so we'll just go to debug folder. Yeah, and then we can see, you know, we should be able to make this, you know. We can always just clean it first, and we can make. So we just want to make sure we can compile here. Looks like it compiled, and then we can maybe run it. We do get some warnings more about yeah, so we see we got some results back. Again, it was pretty quick. Got some testing back. Had some high numbers, so we see some nans, but that's okay. That's just cosmetic. So if we yeah, we can see some of the output. Probably probably look at some of it. HO, let's run. Yeah, CD. This is our output from our test. You don't want to be able to go and see all our market prices. I guess I'll just copy this. Okay. I don't know. Yeah, so we can see we got some results back. Here's the year 1995, July 16th. We had 0 position that day, but we can see the returns, and on we go. So yeah, it looks like everything ran. But again, this is the C++ version. Eventually we want to get the non-C++ version working, and we're going to work in something new called JCUDA. It's going to use the idea of wrappers to put translations or maps or wrappers around the C++ code to get it to run. So We see here the difference is jCUDA, .CUDA, malloc, pointer. It's definitely a little different, the syntax, so we'll have to explore here. And this is jCUDA.org. Don't have this fully working yet, but we'll get it going. Another example of a wrapper is MATLAB, which is a very popular stats package. So we can see here, this is the syntax in MATLAB to interact with the GPUs. And what we expect to see actually is slightly slower run times, because it's kind of one level removed from the native C or C++. So just want to figure out how much of a hit to performance we're going to take. That's part of the testing. And if it's negligible, Java's a great language and we could stick with Java. It's really a big hit, we might have to kind of stay in the C++ world. So again, we're looking at kind of traditional GPU approaches, non-traditional, and everything must compile and run on a foreign server. You can see we're logged in VPN here. So that should really do it. It's really what I love to do, and it's a deep subject, so I could really go on hours, but there's a lot written here, amalgamated over some previous things I've written, so don't want to bore everyone, but I have simple examples, complex examples, so please feel free to look at it. And that is basically it. Thank you very much. Speak to you soon.